The Big Bang was not the beginning. The Big Bang was followed from the remote future. And what happened before was this exponential expansion, because it's just like what we see now in our eon. This theory tells us that there is no beginning and no end, because Einstein originally put it in for two wrong reasons. And he told me, look, you're wrong. And I said, I'm wrong.
The universe you live in might not be the first or the last. According to one of the most brilliant physicists alive, our cosmos could be just one of countless others that have existed before it.
There can be an infinite number of dimensions. And when Einstein heard about it, he did not like it at all. He regarded this as mathematical sophistry. Without that picture, general relativity would be dead. The mathematics has its own existence. We don't create it, we discover it, or we discover parts of it. It'd still be there if there had been no human race. It's so elegant, powerful, universal, and beautiful that they think that the physical world must operate. It's very abstract, but nevertheless it is very permanent.
The Big Bang, he says, wasn't the start of everything. It was a continuation of something far older, something beyond what our minds can easily grasp. And even more astonishing, he believes evidence of that previous universe might already be visible in the sky above us.
Maybe the Big Bang is an interesting event, but not the beginning of time. This reality might be one of many. String theory does have the capacity to describe the world as we know it. Principle is the idea that we could be visited by aliens a crazy idea? No, it's not crazy. If they're a billion years ahead of us, they're not building spaceships and coming to planet Earth because they don't care about us. Maybe the particles do have some kind of version of consciousness, some kind of proto-consciousness, a little bit of consciousness in the electron, in the quark, in the protons. Where does it come from?
In this video, we're going to explore Roger Penrose's revolutionary idea that could completely change how we understand the creation of the universe.
So, Stephen, everyone wants to know, what was around before the Big Bang?
Nothing was around before the Big Bang. According to Einstein's general theory of relativity, space and time together form a space-time continuum or manifold which is not flat, but curved by the matter and energy in it. I adopt the Euclidean approach to quantum gravity to describe the beginning of the universe. In this, ordinary real time is replaced by imaginary time, which behaves like a fourth direction of space.
Mm-hmm.
In the Euclidean approach, the history of the universe in imaginary time is a four-dimensional curved surface, like the surface of the Earth, but with two more dimensions. Jim Hartle and I proposed a no-boundary condition. The boundary condition of the universe is that it has no boundary.
Okay.
In order terms, the Euclidean space-time is a closed surface without edge, like the surface of the Earth. One can regard imaginary and real time as beginning at the South Pole, which is a smooth point of space-time where the normal laws of physics hold. There is nothing south of the South Pole, so there was nothing around before the Big Bang.
The sky above us looks simple until you try to measure it. It stretches without an edge that we can see, speckled with stars that are not points but suns, many with their own worlds. The space between those lights is mostly emptiness, but that emptiness is where most of the mass and energy of the universe lives.
A space-time singularity. Space and time come to a stop.
Yeah, it's about cosmology and about the questions that cosmology raises. So if you're interested in the science of how did the universe begin, even questions of what may have been there, is the universe eternal? Is there such a thing as before the Big Bang? What is the future of the universe? How does complexity emerge spontaneously in a universe? I mean, we sort of take it for granted that there's a Big Bang and it's all hot and there's just this kind of hot glow of stuff. And out of that, spontaneously, in 13.8 billion years, you get something like the Earth with a civilization. and life on it. So how does that, do we know anything about that? I mean, we do. I'm asking the question rhetorically. So it's really about showing the size and scale of the universe, but addressing those questions that I think everybody has about what does it mean to be human, this tiny little finite life that we lead in a possibly infinite universe. How do you make sense of that?
When people speak of the size of the universe, they often point to numbers, billions of galaxies, each holding billions of stars, and distances so large they are measured in light years rather than miles. Those numbers can become hard to hold in the mind, but they do one thing clearly. They show how large and varied the cosmos is, and how small any single human life appears beside it.
We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you've counted, and then you can spread that across the wider universe. And you get this picture of a vast and possibly infinite universe. We know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. Can you picture infinity? Well, no one can picture infinity. We say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. So you can run time backwards, if you like, to find out when they were all on top of each other. It's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. When I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work.
That contrast has been part of human thought for as long as people have looked up and asked, how did all this come to be? People have asked that question in many ways. In ancient times, many answers came from myth and tradition. Those stories put what we see into a larger tale about gods, heroes, spirits, or natural forces acting with purpose. Those answers were written in the language and style of their cultures, and they satisfied immediate human needs to explain the seasons, to justify social rules, to give comfort in the face of loss. As societies developed, other kinds of answers began to appear. Philosophers in Greece and India offered natural explanations for change and order. Centuries later, modern science brought tools and methods for testing ideas about the sky and the ground. Where myth used narrative, science used observation and mathematics. The move from story to measurement accelerated in the last few centuries. When people like Copernicus and Galileo argued that the Earth is not the center of everything, they shifted the scale and perspective of the usual human story. Newton produced laws that could predict the motion of planets and projectiles. The 20th century then rewrote the rules again. Einstein's general relativity changed how we think about gravity. Space and time form a single fabric that bends in response to mass and energy. Those new ideas did not arrive with a single explanation of the universe's origin, but they gave a framework that made questions about beginnings and endings precise enough to test. Early in the 20th century, the idea that the universe had a history became widely accepted among scientists. Observations by Edwin Hubble showed that distant galaxies are moving away from us, and that measurements suggested an expansion. That led to the picture that the universe was once much hotter and denser. The term Big Bang later became a common name for that early hot, dense state. For many people, that phrase raised the same question that myths had raised for centuries. What caused that initial state? Did a thing or being create it, or is it the outcome of physical laws working in a particular way? Scientists interested in testable answers split the question into parts they could study. What does the mathematics of general relativity say about the start of the expansion? How did matter and radiation behave then? What observable traces remain now that could tell us about the deep past?
Einstein's equations require what's called a cosmological constant. It's usually called lambda. These days people call it dark energy, and it causes the universe to expand and expand and expand, and this behavior is in all the cosmology books. If you put in this lambda, the cosmological constant, and when it's positive, that's what it does. So that's pretty well a picture of the universe as we now believe it to be, except people usually think right at the beginning there is something called inflation. This inflation was supposed to have taken part in the universe's activities in the first about 10 to the minus 32 seconds. So think of 1 followed by 32 zeros, 1 over that fraction of a second, in fact, is supposed to have been within the time that the inflation took place. You see, this expansion looks very much like what we see now as this exponential expansion of the universe from the observation of distant supernova stars and all sorts of other things which fit together to get the picture that that's probably what the universe is doing now. But this view is that within these first 10 to the minus 32 seconds, it did this other exponential expansion and expanded by some huge amount in that tiny little point. Now, I never liked this, partly because it didn't fit in with Einstein's equations very happily, partly because, well, it didn't do half the things that it was supposed to do. It's supposed to smooth out the universe, and it doesn't do that. However, if we don't have inflation, you've got to have something a bit like it.
Roger Penrose is one of the figures who shaped how modern physics addresses those kinds of questions. He trained as a mathematician and then turned to problems in gravitational theory and cosmology, using precise mathematical techniques to treat questions about space, time, and singularities. His work in the 1960s pushed forward a way of proving statements about the global structure of space-time. In particular, Penrose produced a result showing that, under broad conditions, general relativity predicts the formation of singularities, places where the usual description of space-time breaks down in a gravitational collapse. That work moved the idea of singularities from curiosity to a mathematical consequence of Einstein's theory. For this and other contributions, he shared the Wolf Prize with Stephen Hawking in the 1980s, and later in 2020, he was awarded the Nobel Prize in Physics for showing that black holes are a robust prediction of general relativity. These honors mark his influence on how physicists think about the extreme behavior of gravity. Penrose's path through science pairs technical work with bold, wide-ranging questions. He has written books aimed at specialists and books aimed at general readers. In The Emperor's New Mind and The Road to Reality, he explored the foundations of physics and mathematics, and he argued about how those foundations relate to mind and computation. He has spent parts of his career at institutions in Britain and the United States and has held distinguished chairs and fellowships. His work spans pure mathematics, applied mathematics, physics, and philosophical commentary. Those mixed interests help explain why he addresses deep questions such as how the universe could begin and what, if anything, preceded the Big Bang. One of the specific ideas Penrose has argued for is a version of a cyclic universe. The proposal, often called conformal cyclic cosmology, suggests that what we call the Big Bang was not the absolute beginning of everything, but rather a transition between one long phase of the universe and the next. In Penrose's picture, the remote future of one cosmic phase, after matter is thinned out and black holes have evaporated, can be rescaled in a particular mathematical way so that it looks like a new Big Bang for the next phase. Penrose uses a mathematical tool called conformal transformation to map the very large, heavily expanded universe into conditions that resemble the hot, dense early universe of the next cycle. The phrase aeon is used for each such long phase. In this schema, our current visible universe is one aeon among potentially many that came before and will follow. Penrose developed the idea over years and presented it publicly in lectures and in his book Cycles of Time. The concept aims to resolve certain puzzles about entropy and to give a consistent account that extends beyond a single Big Bang. The cyclic model is not a small tweak to standard cosmology. It asks for a different way of thinking about the link between the very early and the very late universe. One technical point Penrose emphasizes is that certain physical quantities lose absolute scales in the extreme future. when the universe has expanded so much that only massless particles remain effectively, photons and perhaps other massless fields, you can drop the measure of length and time in a way that makes a long, cold, empty future appear similar to a hot, dense beginning after a conformal rescaling. He argues that processes associated with black holes and what happens to the mass that falls into them are central to making this transition consistent with thermodynamic accounting.
Our galaxy has a black hole which is about 4 million times the mass of the Sun. There are lots of smaller ones undoubtedly going around, but the one at the middle is extremely big. Now, what happens to the black holes eventually? Well, as you see, they evaporate away by Hawking evaporation. And then when they've all gone, how long does that take? Well, for the really big ones, you have to think of something like a googol years. What's a googol? Well, that's 1 followed by 100 zeros. And that's the sort of time you're going to have to wait before all the black holes have gone. The really big ones take the longest to go away, and the smaller ones go away much more quickly. But after they've all gone, now I thought it was pretty boring before, sitting around watching for a black hole to evaporate away. Now that's dead boring. When they're all gone, that's very boring. But then I began to think, who's going to be bored by this? Well, photons probably, mainly photons. And it's really hard to bore a photon. It's hard probably for 2 reasons. One is it probably doesn't experience anything. But the other is from relativity effects, photons don't experience time at all. The time from creation of that photon or whatever happens to it is nothing to that photon. So that it gets right out to infinity, and it's as though this has just happened instantly.
The idea connects the mathematics of general relativity with considerations about entropy and the arrow of time. Penrose and a collaborator, V.G. Gourzadian, also proposed a possible observational signature for their cyclic picture. They analyzed maps of the cosmic microwave background, the afterglow radiation left over from the hot early universe, and reported the existence of concentric rings with unusually low variance. The interpretation they gave was that these rings could mark the imprints of violent events in an earlier aeon, such as collisions of supermassive black holes, whose effects would propagate into the next aeon and leave visible structure in the microwave background. The claim attracted immediate attention because it promised an observational clue to a theory that reaches beyond the usual Big Bang picture. That same claim also sparked careful reanalysis from other teams. Several independent groups examined the data and the methods used to detect the circles and concluded that the reported features were consistent with standard cosmological models and statistical expectations for the microwave background. Those follow-up studies argued that the original analysis had not fully accounted for the statistical properties of the data and that the concentric rings did not rise clearly above expected random fluctuations. This kind of back and forth is common in science. An intriguing claim motivates others to check the methods and to look at newer or more precise data sets. The general conclusion in the community after these reanalyses was that the evidence for the specific ring signature was weak, though that does not by itself invalidate the broader cyclic idea. It does mean the observational support is not settled and that further data and analysis would be required to change consensus opinion. Alongside his cosmological work, Penrose has been careful in how he treats the limits of current theories. He has often pointed out problems he sees in prevailing accounts, including certain versions of inflation theory, which is the standard idea that the early universe underwent a phase of very rapid expansion that smoothed and flattened it. Penrose has questioned some of the assumptions and implications of inflation and has urged the community to remain open to alternative explanations. His tone in these critiques is technical. He raises specific issues about probabilities, initial conditions, and the way certain predictions are compared with observations. That stance has won him respect from some and criticism from others, but it fits the role he has chosen, a mathematician who is willing to take conceptual issues seriously rather than accept a view because it is fashionable. To understand Penrose's view on what created the universe, it helps to separate 2 related but distinct questions. One is about the physical mechanism that produced the early hot dense state we call the Big Bang. The other is about deeper metaphysical or philosophical questions, why there are laws at all or why the specific parameters of physics take the values they do. Penrose's scientific proposals mainly address the first of these. He offers a picture in which our observed early universe is the conformal continuation of a much older cosmological phase. He does not, in his technical work, invoke a supernatural agent or deity. Instead, he seeks a mathematical description that extends beyond a single beginning and fits within the framework of physical law. That is not the same as claiming a full solution to the ultimate metaphysical problem of why existence exists, but it is an attempt to push the scientific boundary on the question of origins. Penrose's argument rests on a mix of geometry, thermodynamics, and astrophysical processes. Geometry comes from his use of conformal transformations, which change the way distances and times are measured while preserving angle relations. Thermodynamics comes in because any account of a cyclic cosmology must explain why the thermodynamic arrow of time, the fact that entropy increases toward the future, appears the way it does. Penrose has long been interested in why the early universe had such low entropy relative to what might have been expected. His cyclic picture is one attempt to reconcile that low entropy initial state with a longer history in which entropy can increase in each aeon, while the conformal map allows a reset of sorts at the boundary between aeons. Astrophysics enters through the role he assigns to black holes and their ultimate decay. The detailed physics of black hole evaporation and how mass and information get dispersed as the universe expands are important to whether the conformal transition is possible. Those layers make the picture complex and require input from several areas of physics to be worked out in full. Critics raise several kinds of objections to Penrose's proposal. Some argue that the conformal matching step is formally attractive but lacks a fully worked out mechanism grounded in quantum gravity, the yet unfinished theory that should correctly describe space-time at the smallest scales. Others point out that the observational evidence cited for the model has not withstood statistical scrutiny in independent analyses. There are also concerns about the role of entropy and whether the required conditions can be realized given what we know about matter and black hole physics. In short, the model contains interesting ideas but also open problems that must be resolved before it could displace or supplement more established parts of cosmological theory. Penrose himself acknowledges these gaps and treats his idea as a research program rather than a finished account. To place Penrose among other scientists discussing cosmological origins, it is useful to mention some contrasting approaches. The standard inflationary model explains several features of the observable universe, such as its near-flat geometry and the statistical properties of the microwave background, through a brief period of exponential expansion driven by a field with specific properties. Other researchers explore quantum cosmology models that try to combine quantum mechanics and gravity to describe the earliest moments in a non-singular way. There are also models that invoke a multiverse, where different regions or pocket universes realize different physical constants or histories. Penrose's conformal cyclic cosmology is one among these alternatives. It differs in emphasis. Rather than adding new fields or invoking a vast ensemble of universes, it reshapes the relation between very early and very late times using conformal geometry. Each idea has strengths and challenges, and the community judges them by their internal consistency and by how well they account for or predict observable features. Penrose's work has also touched on questions that link physics and mind. In books such as The Emperor's New Mind and Shadows of the Mind, he argued that consciousness is not fully explained by conventional computational models of the brain, and suggested that quantum effects might play a role in cognitive processes. He developed a theory in collaboration with Stuart Hameroff, known as orchestrated objective reduction, which proposes a specific kind of quantum collapse occurring in microstructures in brain cells could link quantum mechanics to consciousness. That line of work has been controversial. Many neuroscientists and physicists find the specific biological claims unlikely or unsupported by data, and the quantum collapse idea is debated within physics itself. Still, these proposals show the breadth of Penrose's interests. He moves from the geometry of space-time to questions about the nature of mind and what sorts of physical processes could underlie it. Those efforts do not directly bear on his cosmological model, but they reflect a consistent habit of connecting mathematical thought with questions that seem fundamental to human experience. When new ideas are introduced to explain deep features of the universe, the response from the scientific community usually has several phases. First comes interest and excitement if the idea seems to solve a clear problem or makes a testable prediction. Then other groups try to check the calculations, reproduce the results, and search the data for independent confirmation. If the idea relies on new observations, those observations must stand up to being rechecked with different instruments and methods. If the idea is mainly conceptual or mathematical, then the community scrutinizes the logic and looks for hidden assumptions. For Penrose's cyclic idea, this process has already played out in public. The claimed rings in the microwave background drew attention and then closer analysis, which cast doubt on whether those rings were genuine signals or statistical artifacts. That process is not unique to Penrose. It is how science corrects and refines theories over time. Some viewers will want a direct answer to the question, what created the universe, as opposed to Penrose? The short version is that Penrose does not appeal to a supernatural creator in his scientific work. Instead, he proposes a mathematical and physical framework that aims to extend our physical account beyond a single hot beginning by mapping the remote future of one aeon to the beginning of the next. He looks for mechanisms within physics, the behavior of mass and black holes, conformal geometry, and possible features of quantum gravity that would make such a continuation possible. That is not the same as a final metaphysical answer, and Penrose acknowledges that his work leaves important questions open, especially those that need a more complete theory of quantum gravity or clearer observational signatures. For those who want a physical, natural explanation of beginnings, his proposal is one attempt that moves the question into a form where it can be probed empirically and mathematically, rather than answered by appeal to authority or unquestioned tradition. The historical arc leading to Penrose's ideas helps show why his arguments matter. In the mid-20th century, the combination of relativistic theory and astronomical observation made cosmology an empirical science. Mathematical theorems about singularities showed that simple extrapolations of classical physics predict situations where the theory breaks down. That pushed researchers towards seeking either new physics to smooth those singularities or new ways to interpret them. Penrose's work on singularities, followed by his proposals for cyclic cosmology, are both attempts to grapple with the mathematical consequences of Einstein's theory and with the observational evidence from the expanding universe and the microwave background. His approach is mathematical and conceptual. Start with the equations and the known facts, and then see what consistent extensions are possible. It is a method suited to problems that are hard to test directly because they reach into the extremes of time and scale. What remains unsettled is whether the cyclic conformal picture will become an accepted part of cosmology or remain a thought-provoking alternative. The deciding factors will be twofold: the development of a more complete theoretical underpinning that connects Penrose's conformal mapping with quantum gravity, and the discovery of clear observational evidence that supports predictions unique to that model. Some observational programs, like increasingly precise measurements of the microwave background or gravitational waves, might in time produce data that help discriminate between competing ideas. Until then, Penrose's proposal stands as a serious, mathematically informed suggestion that challenges standard views and pushes researchers to think carefully about the assumptions behind those views. Roger Penrose's career shows the value of bringing mathematical clarity to broad questions. He has built theorems that constrain what theories can do, and he has offered models that try to stretch current theories toward larger explanations. Whether his specific cosmological picture is the correct description of the universe's long-term history is still an open matter, but his work has had a clear effect. It has forced other researchers to state their assumptions more precisely, to refine their statistical methods when working with data, and to consider the relationship between the very early and the very late universe in new terms. Those are practical outcomes. The history of science shows that proposals that do not survive scrutiny can still lead to progress by sharpening the questions and methods used in the field. Penrose's ideas have already done that, and they will likely continue to provoke research and debate for years to come. If Penrose is right, the universe we see might just be one beat in an endless cosmic rhythm. Thanks for watching, and don't forget to subscribe for more deep dives into the mysteries of our universe.